Hello, Precalculus student. This video is for chapter 3.3. We'll look at power function and polynomial function. So what is the definition of a power function? What does it look like? So instead of look at the graph, we'll actually look at the formula first because the formula is very easy. It's a constant k times x to the power p. P is a power. So strictly speaking, if it's a power function, x to the p can be any number. So you can have, for example, f of x equal to 3 x to the 1/2. This is square root x, right? You can have x equal to -5, just a constant, and then x to the 4th power. So these are all called power function. It's a lot like yours, direct variation, y vary directly with a certain power of x like that. So we're interested looking what is the shapes of graph of power function when the power is a whole number. So we know the definition of whole number is positive integer, such as 1, 2, 3. So no more 1/2 or whatever, always just whole numbers. So for example, x squared, x cubed, these two are actually part of the two-kit function. We already know the shapes of this function. If x squared is just, parabola goes up, and if it's x to the cube, it is kind of like the S shape, right? So when x is really small, like -1 million, when I say really small, I mean really negative, y still goes up. Y goes up at the two end, no matter what, right? So we would use this notation. We say when x approaches, not equal, but approaches a infinity, very big number, y, f of x is y, would approaches also infinity because this is infinity. Y is going to infinity. When x approaches negative infinity on this side, f of x also approaches infinity. They go to infinity on both sides, right? Rise to the left, rise to the right. But whereas in the x cubed function, it doesn't bend because what happens is if you consider the table of value, when x is, say for example, very big, 1000, okay, and then you cube it, it's still positive, right? It's really, really big, 1000. I don't know what, 100,000? No, 100 million. Okay, so when it is 0, it's 0. But when x is negative, right, it doesn't go up anymore because when you cube it, it's still negative, right? It's still very, very negative. So in general, we describe this phenomena as when x approaches infinity, f of x is the same, approaches the same infinity. But when x approaches negative infinity, that means really, really negative, f of x is still negative. So x and y goes the same direction in terms of infinity. Whereas for a square, even power function, because when you square a negative number, it's still positive. So in general, we can make this conclusion for kx to the n, where n is a whole number, k is a constant. So if I have a special power function where n is an even power of a whole number, then I can say when so I can say the shape of the graph would be like this. So when x approaches infinity, f of x approaches also infinity. They go, no matter what, they goes up, okay? Because it's even power, and the coefficient y equal to k. K is the coefficient x to the n. So for example, you can think of it as y equal to 3 x squared. So of course they go to infinity. When x approaches negative infinity, I don't have to think. No matter you go to which infinity, it's just going to be positive because it's going up. Now, but when the coefficient is negative, there's a reflection, right? So reflection over the y-axis. So your graph all of a sudden become like this. So even if it is 4th x to the 6th, they're just in general like this. You can use decimals to look at the difference between I have decimal here. So if I say y equal to x squared, so that's look like this. Y equal to x to the 4th. So this is all the even number. So it's just, shoot up faster. But you can see that it is still going to y equal to x to the 6. So you can see the green one is really, the point of intersection is 1, 1, negative 1, 1, 1, and 1, negative 1, 1. So because when you multiply negative 1 6 times, it's still 1. So, but then it just shoot up faster. So by looking at the graph and also by building table, you can tell if you have a negative number. Okay, if I put them negative, okay, let's do negative 3. Oh, suddenly it flip over because that's negative 3. So they all flip over because of a reflection. Okay, so when you have even power, but then your coefficient k is negative numbers and it shoot down, we would describe this be phenomena as x when x approaches infinity, f of x, no matter what, always negative infinity. And when x approaches negative infinity, f of x also approaches negative infinity. No matter what, it's just negative. It's always positive. What about odd power? So let's use decimal to look at it. So let's say x cubed. We know x cubed is this way. I'm going to delete this. And then so it would shoot up when x is positive infinity, shoot down when x is negative infinity. What about x to the 5? Let's not do this. Oh, here. X to the 5. X to the 5 is the blue one. So it's in general the same shape, but just shoot up faster. They intersect at 1, 1, they shoot up faster. So if you look at the intersection, so before negative 1, the x to the 5 like lower below x cubed, but when it is after 1, 1, it shoot up faster. So what about x? What is a good number? X 11. So all this odd power, if I turn this up, turn it on, so you can see that it's shoot up very fast after it passed through 1, 1. But so the local behavior is a little different, but the end behavior are more or less the same. So let's look at this. Look at this, how to describe it. So if it is a is positive, like y equal to 2x to the third, so it'd be like that, right? So it's still like this. Just a vertical stretch. We say when x approaches infinity, f of x what? It's the same as what x is, also approach infinity. But when x approaches negative infinity, f of x also approaches negative infinity. So they go different direction as x. X goes positive, it goes positive. X goes negative, it goes negative. Because when you do an odd power, you will have a negative when you are inputting a negative. And what about when you have the coefficient being negative? Then it is a horizontal, no, it's a vertical reflection. So this become down, the left-hand side become up. So we would imagine something like this, right? So when x approaches infinity, on this side, actually f of x go to negative. They actually go different direction. And when x approaches negative infinity, like on this side, you negative, negative, f of x equal to infinity. So they flip, right? And the general shape is like this. So there is only 4 cases for y equal to k x to the n. They are either up, up, down, down, or rise to the right, drop to the left, or rise to the left, drop to the right. Depends on the coefficient and also the power. So this table summarizes that. Let's try. What is the end behavior of negative 3x to the 6? So we say 6 is even power. We know that it is even either up, up, or down, down. Is it up, up, or down, down? But k, which is the coefficient of the power function, is negative 3 is less than 0. So when x approaches infinity, f of x would approaches, no matter what, it's always going to be negative because you have a negative that's multiplied in front of it. When x is negative infinity, f of x also negative infinity. They always go down, right? Like that. Always go down like that. So that is the kind of the behavior of power function. Why do we learn power function? Because the behavior of the polynomial function is very similar to the power function in the end behavior. So when we investigate polynomial function, there is the behavior of a term actually determine the end behavior of the polynomial function. So if I graph a polynomial function, what does it look like? So it turns out that the graph of a polynomial function is a smooth curve, and it would turn locally. There's a local behavior as well as an end behavior. So maybe I would talk about the end behavior first, and then we'll talk about local behavior later, okay, in the next video.